Welcome to the last part of week 3. We talk today about power functions and polynomial functions. Let's start with the definition. By a power function, we mean a function of the form constant times x in a natural power. So when I write k times x to the power p, I mean here that k is a non-zero constant, a real number that is not zero, and p is a natural number. Remember, boldface n is the set of positive integers. K here is known as the coefficient, and the definition of a polynomial function is also very similar. A polynomial function is an expression of this form, powers of x, with numbers in front of them. The number a sub n is not zero. These numbers are called coefficients. A sub n is called the leading coefficient, and a sub n times xn is called the leading term. Naturally, any power function is a polynomial function. Also, another comment here, naturally a quadratic function. The one of the form ax squared plus bx plus c, where a is not zero, also is an example of a polynomial function. Note here that a being non-zero, the coefficient in front of x in the highest power, is the leading coefficient. So ax squared is the leading term. In fact, even linear functions are also polynomials. A function of the form mx plus b, where m is not zero, is also a polynomial function. This number n here is called the degree of the polynomial. So the quadratic function is a polynomial of degree 2, and a linear function is a polynomial of degree 1. Provided, of course, that m, which is slope, is not zero. Let us give a variety of graphs of power functions. For the function x to the power p, where p is an even integer, 2, 4, 6, 8, all of these functions have a similar look. They all are kind of parabolic shaped. And you can also see from the picture that the higher the power, the greater the function is if x is by absolute value is more than 1. So in this picture, the one on the left, naturally if x by absolute value is greater than 1, then x in the higher power, x in the power p1 is greater than x in the power p2 if p1 is greater than p2. That explains, for instance, why the blue graph, which corresponds to x to the power 4, is above the green graph, which corresponds to x squared, outside the interval negative 1, 1. We can explain why this is the case, because this inequality, x to the power p1 greater than x to the power p2, is logically equivalent to x to the power p1 minus x to the power p2 greater than 0, which is logically equivalent to, let us factor out p2. So that in parentheses we have x to the power p1 minus p2 minus 1 greater than 0. Now, when is the product greater than 0? If and only if either both cofactors are positive or both cofactors are negative. So either x to the power p2 is greater than 0 and x to the power p1 minus p2 greater than 0, or both are negative. Well, because p2 is even, x to the power p2, x to an even power, is never less than 0, so that system is inconsistent. I made a mistake here. It should be minus 1 greater than 0 and minus 1 greater than 0. The second system is inconsistent, so we must have the first system. The first inequality in the first system is automatically true, so we must therefore have x to the power p1 minus p2 is greater than 1. So that is logically equivalent. Remember, p1 is greater than p2. And both are even numbers, so their difference is also an even number. Either x is greater than 1 or x is less than negative 1. Now, we have the opposite situation. And by the way, how about the reverse direction? If x is greater than 1 or less than negative 1, then absolute value of x is greater than 1, and x to the power p minus 1 minus p2 will be greater than 1 if p1 minus p2 is greater than 0, and less than 1 if p1 minus p2 is less than 0. So we establish the other statement. Once again, the function with the higher power will be above the function with the lower power if x by absolute value is greater than 1. We have the opposite situation when x by absolute value is less than 1. So you can see that the blue graph is below the green graph. The blue graph corresponds to the fourth power, and the green graph corresponds to the second power. The second power beats the fourth power when you are in between -1 and 1. You can show this fact using the same work. In principle, all these are parabola-shaped. For the odd powers, they're all shaped like cubic parabolas. And again, you can see that whenever x by absolute value is greater than 1, the higher power, say power 7, the red graph, will beat the lower power, say the green graph. But in between -1 and 1, you have the opposite situation, and we can check that. If x by absolute value is less than 1, and say P1 greater than P2, where both are odd and positive, x to the power P1 will be less than x to the power P2. Again, you can show this using the same type of reasoning, and it's very clear in the picture. Once you are at a distance less than 1 from the origin, the higher power loses to the lower power. The green function beats the red function, even though the green function is x cubed, whereas the red function is x to the 7th power. That is to keep in mind. Now let us talk about what's called the end behavior of power functions. In many applications, it is important to know how power functions behave when x is very, very large positive or very, very large negative. Again, we're looking at functions of the form k times x to the power p. K is a real number other than 0, and p is a natural number. To describe end behavior, we use special notation. We will say that x approaches positive infinity and write x approaches positive infinity to mean that x is allowed to take arbitrarily large positive values. And likewise, we will write that x approaches negative infinity if x is allowed to take arbitrarily large negative values. Now, there's a tiny bit of confusion here because occasionally people also write x approaches infinity without sign to mean that x is allowed to take either arbitrarily large positive values or arbitrarily large negative values. Anyway, we will be interested in what happens with the expression k times x to the power p. That's our f. What happens with f? What kind of values will f take when x is allowed to grow without bounds, either in the positive direction or in the negative direction? In other words, we will write that limit of f at, say, negative infinity is negative infinity, and write literally lim f of x at x approaching negative infinity is negative infinity, to mean that whenever x is allowed to be infinitely large negative, negative 1000, negative million, negative billion, and so on, the values of f also become arbitrarily large negative. Accordingly, we will write that limit of function f as x approaches infinity is infinity if f can be made arbitrarily large by choosing x arbitrarily large. Of course, nothing prevents us from considering other combinations, say limit of x approaching negative infinity being positive infinity and vice versa. This means, for instance, that the value of f could be made arbitrarily large by choosing appropriately x as a very large negative value. And accordingly here, as x approaches positive infinity, meaning x is allowed to take arbitrarily large positive values, values of f become infinitely negative. So we can see from this picture that the functions of the form x to the power 2k, where k is a positive integer, namely x squared, x to the fourth, x to the sixth, x to the eighth, x to the 10th power, x to the 12th power, at infinity all behave in a very clear way. All of these are parabola-shaped graphs, and no matter what sign of infinity x is approaching, positive infinity or negative infinity, it's very clear from the graph that the limit of x to the power 2k with x approaching plus or minus infinity is always positive infinity. If x is very, very large positive, so is x to the power 2k. If x is very, very, very large negative, so is x to the power 2k. Now, all of these could be written generically as x to the power 2k plus 1, where k is a positive integer. So these are functions x cubed, x to the 5th, x to the 7th, x to the 9th, and so on. And again, from the picture, we see immediately that they all behave in a very particular way. Whenever x is huge positive, so is the value of f. And whenever x is huge negative, so is the value of f. Right? When x is huge positive, so is the value of f. When x is huge negative, so is the value of f. Now, more generally, we have this type of diagram. The end behavior of power functions depends entirely on the sign of the coefficient k and the parity of the power p. Parity means even or odd. So let me remind you again that this is here k times x to the power p. K is non-zero real number. p is a positive integer. And so depending on p, whether p is even or p is odd, and whether k is positive or negative, we have the following type of end behavior. So when the constant in front of x is positive, we have either function behaving like x squared, or a function behaving like x cubed, depending on the parity of p. And naturally, when k is negative, this changes to the opposite behavior. You can think of this as being negative x squared, negative x to the fourth, negative x to the sixth, and of this as negative x cubed, negative x to the fifth, negative x to the seventh, and so on. Again, the fancy way of writing this is this. Limit of k times x to the power n. For some reason it's n now, not p, is either positive infinity in the case when k is positive and n is even, that's this situation, or negative infinity when n is even and k is negative, that's this situation. Note that we have positive infinity, for instance, regardless of where x is approaching, or negative infinity regardless of where x is going. When the power is odd, the situation is a little trickier. For positive x's, and odd power, for positive constants and odd power, we have the function going in the same direction as the argument. Whenever argument goes to positive infinity, so does the function. Whenever x goes to the negative infinity, so does the function. It's vice versa when the coefficient is negative. So x going to negative infinity implies f goes to positive infinity, and x going to positive infinity implies that f goes to the negative infinity. Okay, let us now talk about polynomials in greater detail. Well, first of all, know that graphs of polynomials are continuous, meaning that they can be drawn without lifting the pen from the paper, and also they're smooth, they have no sharp angles. So in the picture on the right, in the picture below, this graph has a sharp angle. It could be the graph of some absolute value function. It is therefore not smooth, and so this cannot be a graph of a polynomial function. A similar situation is here. We have what's called a discontinuity here. The graph of this function cannot be drawn without lifting the pen from the paper. And because of this discontinuity, this cannot be the graph of a polynomial function either. The two graphs on the left could be, potentially, graphs of polynomial functions. This cannot be established just by looking at the picture, though, because we don't know what happens after that. There could be a discontinuity somewhere where we don't see this graph. But from what we see, this could be. In many problems, it's important to find roots of a polynomial function, which is in general is a difficult problem, although occasionally, like in these two examples, it's possible to factor your polynomial and find the roots or zeros, as they're called. For example, in 15, we can, if we equate this to 0, we can factor out x squared. And so the expression in parentheses will be x to the power 4 minus 3x squared plus 2. And if we equate this to 0, we see immediately that either x is 0 or the expression in parentheses, which is x to the power 4 minus 3x squared plus 2, must be 0. This is what's known a biquadratic equation. It easily becomes quadratic if we set x squared to be t. Of course, t is then has to be non-negative. Once you do that, the equation becomes t squared minus 3t plus 2. And you can easily find the roots. The roots are 2 and 1. Both are non-negative. So when you solve x squared equals 2, you have x equals plus minus root 2. And when you solve x squared equals 1, you find x equals plus minus 1. So this function f here factors completely. We know it's x squared times x minus 1, x plus 1, x minus root 2, x plus root 2. We have 5 zeros, or 5 roots, plus minus 1, plus minus root 2, and 0. In example 16, it's also possible to find the roots of polynomial f. It's a relatively simple problem, because if we equate to 0 this expression x cubed minus 5x squared minus x plus 5, and know that we can group the terms, we can group the first two terms and the last two terms. And in the first two terms, we can factor out x squared, to get x minus 5 in parentheses. Now x minus 5 is a common factor, and what's left in parentheses is x squared minus 1. And factoring, we get x minus 5, x minus 1, x plus 1. So the zeros are x1, -1, or 5. Naturally, when the graph of some function crosses the x-axis, which happens exactly where f is 0, there could be two different situations. The graph could cross over the x-axis, or the graph could touch the x-axis without crossing it. And we will now investigate when either of these two situations happens for polynomial functions. Here is one example. We have a factored polynomial x plus 3 times x minus 2 squared times x plus 1 cubed. And as you see, at root -3, we have a crossing. At root 2, we have a touching. And at root -1, we have a crossing again. The following theorem establishes the necessary and sufficient condition for touchings and crossings. Suppose when our factored polynomial has a factor of the form x minus h to the power p. The behavior near the root x equals h is determined completely by the power p. Namely, whenever p is even, we have a touching, and whenever p is odd, we have a crossing. Moreover, in either situation, we call h as 0 of multiplicity p. So we can say that the graph of a polynomial function will touch the x-axis at zeros with even multiplicities, and it will cross the x-axis at zeros with odd multiplicities. So 2 in this example is a multiplicity of 2. And -3 is a multiplicity, is a root, or 0 of multiplicity 2, and -3 is a root of multiplicity 1. That is because this factor x plus 3 is raised to the power 1. Likewise, -1 is a root of multiplicity 3. And we can clearly see that wherever we have multiplicity even, which in our example is root 2, which is of multiplicity 2, and 2 is even, we have a touching. Don't get confused here. It has nothing to do with the number 2 here being even. It's not the roots whose parity we are looking at. It's the powers to which these factors are raised. The roots -1 and -3 are both odd multiplicity. Namely, -3 is a root of multiplicity 1, and 1 is an odd number. And -1 is a root of multiplicity 3, and 3 is an odd number. And 2 is, of course, an even number. So once again, the graph of a polynomial function will cross the x-axis at zeros of odd multiplicity, and it will touch the x-axis at zeros of even multiplicity. Let's look now at this new example. We are given a picture, and it's known that this is a polynomial of degree 6. Well, let's say this is a polynomial function of degree 6. Identify the zeros and their possible multiplicities. And I would even add here, find possible forms of f. Where are the zeros? Well, the zeros are -5, excuse me, -3, -1, and 4. Moreover, we see immediately that because at -3 we have a touching, that has to be a root of even multiplicity. And because at -1 and 4 we have crossings, these two are odd multiplicity. Now, what are the possible forms of this function? Well, because the function is of degree 6, the multiplicities of these 3 roots must add up to 6. So what are the ways to write 6 as a sum of 3 numbers, of which one is even and the other 2 are odd? One way to do this would be 4 plus 1 plus 1. So it could be that -3 is a root of multiplicity 4, -1 is a root of multiplicity 1, and 4 is also a root of multiplicity 1. -3 cannot be a root of multiplicity 6 because then -1 and 4 would have to be roots of multiplicity 0, so they wouldn't be roots at all. Naturally, -3 cannot be a root of multiplicity more than 6. So we can only look at multiplicities less than 4. And it has to be even, so it's possible in principle that -3 is a root of multiplicity 2. But then the other two multiplicities must add up to 4, and they must be both odd. So it's either 3 and 1 or 1 and 3. These are the only three ways how these roots could have their multiplicities adding up to 6. So the corresponding possible forms, let's call them 1, 2, and 3, are the following. F could have root -3 with multiplicity 4 and the other two roots with multiplicity 1. In general, it could be multiplied by some constant other than 0. That's one possibility. Another possibility for F is that -3 is a root of multiplicity 2. -1 is a root of multiplicity 3. And 4 is a root of multiplicity 1. The whole thing is then multiplied by some constant k2. And the third possibility is that -3 is a root of multiplicity 2 again. -1 is a root of multiplicity 1. And 4 is a root of multiplicity 3. These are, in principle, the only three possible forms of the polynomial function whose graph we see on the left. Which would require further analysis. We don't do it here. Much like for power functions, it will be of great interest to us to look at end behavior of the polynomial functions. Surprisingly, the end behavior of a polynomial function is completely determined by the leading term. By which I mean that the influence of other terms is negligible. The other terms don't affect the end behavior of the polynomial. Specifically, forgetting about other terms, the end behavior of this polynomial is exactly the same as the end behavior of the leading term, which is a power function. We talked just now, a few minutes ago, that everything depends on the sign of the leading coefficient and the parity of the degree. If the degree is even, the end behavior of the entire polynomial is determined by the sign of a sub n. It's positive infinity if a sub n is positive and negative infinity if a sub n is negative, regardless of where x goes. In case when the degree of the polynomial is odd, the behavior of the polynomial depends on where x goes. For positive coefficients, x going to positive infinity implies the function goes to positive infinity, and x going to negative infinity implies that the function goes to negative infinity. For negative coefficients, it's the other way around. In short, the end behavior of a polynomial function is completely determined, or actually is exactly the same, as the end behavior of its leading coefficient, of its leading term. And the picture on the next page demonstrates this again. Whenever the degree of the polynomial is even and the leading coefficient is positive, we have at both infinities positive infinity with something going on in between, and the horizontal reflection of this, or rather vertical reflection of this, when the leading coefficient is negative. It could be any kind of behavior in between infinities, but at both infinities, negative and positive, we have the function going to negative infinity. When the degree of the polynomial is odd, the polynomial behaves like the cubic parabola, either the positive cubic parabola or the negative cubic parabola. In other words, positive at positive infinity, positively infinite at positive infinity, negatively infinite at negative infinity, or reflect that about the x-axis. So positively infinite at negative infinity and negatively infinite at positive infinity. For example, determine the end behavior of the following functions. In both examples, these are polynomial functions. And for example A, we see immediately that f is a polynomial of what degree? F is a polynomial of degree 4, because this is a linear term. This is also a linear term. When you multiply x by x, it will be x squared plus terms of lower powers. And when you multiply this x squared by this x squared, you get x to the 4th power, and it will never be a power more than 4. So f is a polynomial of degree 4. In fact, f is negative 3x to the power 4 plus some terms of degree fewer than 4. And we don't need to know what those terms are because, again, the end behavior of a polynomial function is the same as the end behavior of its leading term. The leading term is negative 3x to the power 4. So we are in a situation like this. The degree of the polynomial is even, it's 4. The leading coefficient is negative. So whether x goes to positive infinity or negative infinity, our function f at either infinity is negatively infinite. Now for example B, we have g, a polynomial of degree 3. It's a product of 3 linear factors. When you multiply x by x by x, you get x cubed, and you will never get powers of x greater than 3. So x is a polynomial of degree 3. So in fact, g is, when you multiply x by x by x, you get x cubed, and then that is multiplied by 0.2, plus, again, some terms of degree fewer than 3. The leading term is 0.2 times x cubed. The coefficient is positive, the degree is odd, and so we are in a situation like this, like cubic parabola. Our function f will be positively infinite whenever the argument is positively infinite, and it'll be negatively infinite whenever the argument is negatively infinite. All right. Another fact about polynomials that you will need to know is the bounds on the number of zeros and the number of local extrema. Local extrema is the plural of extremum. An extremum is a point of local maximum or local minimum. This would be a local maximum, a point near which values of your function are smaller than at the point itself, and local minimum, a point near which the values of your function are greater than at the point itself. So the question is, how many zeros can a polynomial of degree n have? And how many local minima and maxima can a polynomial have? Well, the theorem is this. A polynomial of degree n can have at most n roots and at most n minus 1 points of local extrema. Note immediately that the theorem doesn't say that a polynomial of degree n must have n roots. It's easy to give an example of a polynomial that has no roots at all. For example, consider the quadratic function x squared plus 1. It is a parabola, x squared raised upward by 1 unit. It never intersects the x-axis, and this polynomial has no roots at all. This theorem simply says that any quadratic cannot have more than 2 roots, but it might have less than 2 roots, definitely no more. Same for extrema. The theorem does not say that any function must have, any polynomial function of degree n must have exactly n minus 1 points of local extrema. That's false. Consider, for instance, the function x to the power 4, which is of degree 4. How many points of local extrema does it have? Exactly 1. Degree is 4, n minus 1 would be 3, but it doesn't have 3 local extrema. It has exactly 1 extremum. All right. Let us briefly look at the graphs on this page. So the polynomial here is of degree 5, leading term is 5x to the power 4. So you can therefore, when determine the behavior, the end behavior of this polynomial function, forget about the other terms and conclude that this polynomial function behaves at infinity simply like its own leading term, 5x to the 4th power. And that behaves just like x to the 4th power, infinity, positive infinity, either direction. This here is a polynomial of even degree, 6. The leading coefficient is -2, so it behaves like the vertical reflection of the first picture. Reflect that about the x-axis, you will get this. Note that the behavior between infinities is pretty complicated. There are extrema, but at infinities, the function is negatively infinite because this is how its leading term behaves. In this example, we have a polynomial of degree 5, whose leading coefficient is 3. So the whole thing behaves like a cubic parabola, positively infinite at positive infinity, and negatively infinite at negative infinity. This here is a polynomial of degree 3, with leading coefficient -6. And so it must behave like a negative cubic parabola. So the graph on the right is therefore wrong. It should look like negative cubic parabola, perhaps with some weird behavior in between, but definitely not like this. It should be negatively infinite. At negatively infinite at positive infinity, and positively infinite at negative infinity. All right, now in example 20, without graphing the function, determine the maximum number of x-intercepts and local extrema. Note that this is a polynomial of degree 12. This is the largest power. So f has at most 12 zeros and at most 11 points of local extrema. according to the theorem. And a few more examples. Another biquadratic equation. If you want to find the x-intercept, for instance, for x-intercepts, you need to equate this to 0. X to the fourth minus 4x squared plus, negative 45 equals 0. For that, you set again x squared to be t, and t has to be non-negative. So we end up with t squared minus 4t minus 45 equals 0. I wonder if the roots are rational, maybe not. Using the formula for roots of a quadratic equation, we have 4 plus minus 16 plus 4 times 45. So the roots, it looks like, are not rational. 4 times 45 is what? 160 plus, they could be rational, plus 20, which is 180, and 180 plus 16 is 196. 196 is the square of 14, I believe. So one root is 4 plus 14 over 2, that is 18 over 2, that's 9, and the other root is negative 5. The root negative 5 we should ignore because we're only looking for roots that are non-negative. And when t is 9, x squared is 9, so x is plus minus 3. So x-intercepts are at negative 3, 0 and 3, 0. Y-intercept is, if you substitute 0 for x, you will get negative 45. So y-intercept is at 0, negative 45. And in the last example, we need to sketch, without using Desmos, obviously, the graphs of these two polynomial functions. It won't be an exact graph, only a sketch. So the roots of f are negative 3 and 5. Negative 3 is a root where we have a touching, and 5 is where we have a crossing. Also, what about the end behavior? To understand the end behavior, we need to identify the leading term of f. Well, f will be the polynomial of degree 3. If you were to expand the parentheses, this would give you x squared times x, that is x cubed times negative 2. And there will never be any terms of degree higher than 3. So f will behave at infinities like negative cubic parabola. Infinitely positive at negative infinity and negatively infinite at positive infinity. So we can draw the graph. Okay. Now, how about the graph of G? Again, we need to identify the roots. The roots are 1 and negative 3. And 1 is a root of even and 0, right? Also 0. 0 and negative 3 are roots of odd multiplicity. So it follows that 0, 0 and negative 3, 0. At this point, we have crossings. And also x equals 1 is a root of even multiplicity. Why is that? That is because x minus 1 is raised to the power 4, and 4 is an even number. So at the point 1, 0, we have a touching. Now, how about the end behavior? So let me write again here. The end behavior here was at negative infinity, we have positive infinity, and at positive infinity, we have negative infinity. The end behavior of G is again determined by the leading term of G, which is 1/4. If you were to expand all parentheses, here the highest term will be x to the 4th power. Here the highest term would be x to the 3rd power. And so it would have been 1/4 times x to the 4th times x cubed plus terms of degree smaller than 8. And this is 1/4 x to the power 8. 8 is even, 1/4 is positive. We will have a behavior like this. So now we're ready to make our sketch. Crossings at negative 3 and 0. And a touch at 1. Note again that this is only a sketch. We can't, for instance, know that the graph won't look like this, for instance. Although we kind of know that it can't look like this, because this is a graph of degree 8. It cannot have more than 7 points of local extrema. Still, there is a great deal of freedom here. We could have local extrema here, maybe some here. So our analysis doesn't show whether it's the purple curve or the green curve that we should have. We only determine the end behavior and the roots and the type of intersection at the roots, either crossing or touching. All right, this marks the end of week 3. Thank you for your attention.